Hey guys, so you guys just ducked out the door. It's snowing out, and just a couple of little reminders here before I finish off the last couple of slides of things that we were going to try to finish today, but obviously that didn't happen. First thing is this: if you did not pick up your packet of old exams and quizzes or your review sheet and note card. The sub will have that for you on Monday. I'll get those in packets and I'll get them for the sub to hand out to you on Monday with your names on them and all that good stuff. That won't take me too long. So make sure you grab that on Monday from the sub. Remember, Monday, you guys will work on the trends worksheet and the take-home quiz. The sub will hand that out to you on Monday, okay? Behave on Monday, then Tuesday, trends worksheet, take home quiz, you'll hand it to me, and then we'll kind of go from there. So big thing is, if you didn't get those review sheet, note card, and then all of your old exams and quizzes, I've already got them clipped up and ready to go. Ask for them from the sub on Monday, okay? And then that's it. So let me go to now to start, whatever, 5-10 minutes here of sort of a video lecture here on the electronegativities that we got to wrap up from yesterday. All right, let me share my screen here. Boom. Okay, so you guys should be seeing my whiteboard screen. So, we left off yesterday talking electronegativity, right? And this is this measurement of the ability of an atom to attract towards itself electrons in a chemical bond. So it increases from left to right, and it decreases down in a group. So again, I'll ask it like we talked about with atomic radius or ionic radius. I'll give you either three elements that are within a column, a group, or three elements along a period from left to right. And you'll have to tell me, which one has the largest electronegativity or lowest electronegativity. But furthermore, right, we talked about how we can use electronegativity to determine what type of bond exists between two atoms, right? So nonpolar electrons are shared equally, polar electrons are shared unequally, because in the case of this example that we talked about yesterday, we talked about the oxygen is more electronegative, so the electrons get pulled towards the oxygen, causing the oxygen to have a slight negative charge, and the hydrogen's opposite to have a slight positive charge. So that's the polarity of a polar covalent bond. And then in ionic bonds, electrons become completely stripped, okay? And we talk about being very polar. It's so very polar to the point that the electron is going to be completely lost to the negative ion. Here's chloride, right? Taking that negative, here's chloride taking that electron from sodium. Sodium becomes +1, the chloride becomes -1, okay? So how do we determine the bond type? We can use just a simple math, right? Simple subtraction. So this sheet, right, that you guys got for me, it's got the electronegativities on it, right? All you have to do is subtract the difference between the two atoms involved in a bond to predict the bond type. If that difference is less than or equal to 0.4, then it's going to be nonpolar covalent. If it's 0.4 to 2.0, it's polar covalent. And if it's greater than 2.0, then it's ionic, okay? Now, like I said yesterday, I kind of alluded to this as we walked out of the room. You guys are smart kids, and you kind of look at this and you go, well, less than or equal to 0.4, and then 0.4 appears here. Greater than or equal to 2.0, and then 2.0 is the top end of the polar covalent section. So what about kind of the in-between times, right? We're going to talk about that in just a second. Before we do, let's work some quick examples so you guys understand how we can use electronegativity difference to figure out which of these bonds can you predict is going to happen between two atoms, okay? All right, so just to prove a point like we kind of talked about yet. So here's nitrogen. So nitrogen forms a triple bond between it's an N2 molecule, right? It's got two nitrogen atoms bonded to one another. The electronegativity of nitrogen off the chart is 3.0. Well, 3.0 minus 3.0 is 0. The difference is 0. So 0 would put me less than or equal to 0.4, so it is a nonpolar covalent bond, right? And if you think about it, it makes sense. It should be a non-polar covalent bond. You know, I've got two nitrogen atoms that have the same electronegativity. They're identical, right? Neither one of them is going to have any more greater or less pull on the electrons. They're going to be shared completely and utterly equally. Okay. Now, let's look at hydrogen and oxygen in water. So H2O. We talked about water being a polar molecule or containing polar covalent bonds, but let's prove it using the numbers, right? So the electronegativity of oxygen is 3.5. That's right off the chart. The electronegativity of H, hydrogen, is 2.1. 3.5 minus 2.1, right? And you always subtract the smaller from the bigger. The oxygen is the more electronegative one, right? The difference is 1.4. Okay, so 1.4 means it's sort of smack dab in the middle of the polar covalent bond section. It would be considered a polar covalent bond, okay? And again, that means that the electrons that are being shared between the hydrogen and the oxygen are going to be being drawn towards the more electronegative atom, and that is oxygen in this case, okay? And then again, last one, right? Last example here, sodium and chlorine. So if I were to form a bond between sodium and chlorine, what kind of a bond would it be? The electronegativity for sodium is 0.9. Again, that's right off the chart. And I'm not going to show it here. You guys could look it up. And then for chlorine, it's 3.0, right? Again, right off the chart. Okay. 3.0 minus 0.9 has a difference of 2.1. Okay. So that puts us in the ionic section, right? It's above 2.0. It's definitely in the ionic section. We know that sodium chloride is an ionic compound. It contains a metal and a non-metal anyway. But again, we're proving a point that it's in the ionic bond section according to the calculating the difference between the two. Which again means, the chlorine is much more significantly electromagnetic or electronegative. Gosh, I can't speak. Meaning that the electron is going to be lost and completely stripped from the sodium and becoming part of the chlorine to make it the chloride minus one ion. Okay. Now back to that kind of question at hand, right? What if it's like in the border between these two that we talked about, right? So I got a couple of examples that we can talk about that you got to kind of make a decision. You got to kind of maybe explain yourself, right? And it is very, very certainly true that not every bond in the universe is going to perfectly fit within these three categories. Some are kind of in the middle, right? And some we're going to have to make some decisions and make some explanations about them. So like, for example, one example, carbon and hydrogen in CH4. CH4 is methane, like methane gas is natural gas, okay? So we use it, in the Bunsen burners that we burn, right? Okay. So it's, it's a molecule of central carbon atom, and it's got four hydrogens kind of shooting off of that or bonded off of that, right? The carbon's electronegativity is 2.5. Hydrogen's electronegativity is 2.1. Again, I got that right off the chart, right? Which again, you guys don't need to memorize this chart, right? But 2.5 minus 2.1 is 0.4. Okay. So, it's sort of right in the middle, right? It's right in the middle of this. It's 0.4. Well, what, do we call it non-polar? Do you call it polar? You could probably explain and say, in this case, it's, you would say that it's maybe, I wouldn't go so far as to say it's completely non-polar. You would probably explain that type of bond is maybe very slightly polar. Saying that is completely okay, right? Like explaining it that way is completely okay. Because again, it is kind of caught in the middle. The carbon is a little bit more electronegative. There's a chance that those electrons are going to spend a little bit more time around them, right? Making it maybe the very slightest polar, okay? Down here, another example. So potassium and bromine in like KBr, right? Potassium is 0.8, bromine is 2.8, okay? Sorry, that's an ugly looking 8, but that's 2.8, my bad, okay? Well, the difference, 2.8 minus 0.8 is 2.0, okay? So again, this is right on the border. Like, is it polar? Is it 2.0 polar? Or is it 2.0 ionic? Okay. Well, this one's a little bit better to kind of, we can make a decision on it. I want you to think about it for a second, right? I would definitely lean on saying that this is definitely ionic. Okay, this is an ionic bond between the two, even though it's kind of right on the border. Again, what's the clue for me to be able to say that this is an ionic bond? Well, I've got a metal in the first position and a non-metal in the second position. So it's on the border. It means that bromine is maybe not quite the same level of electronegativity that we see in all ionic bonds, or comparatively in all these ionic bonds. But this is a metal non-metal. This is definitely an ionic compound. It's on that border. Okay. Now, let's say we are on that border, right? And the two elements, and let's just say element X and element Y. Let's say we're on that 2.0 border, and the two elements, okay, neither of them are metals. Okay. Well, then I would lean on calling it probably polar covalent. Because if they're non-metals, remember, metal and non-metal equals ionic in our naming system. Well, if it's 2.0, it's right between, right, that 2.0, okay, and both of the elements involved are non-metals, then that means they're molecular substances that contain some level of covalent bond, okay? So then I would say, hey, it's a polar covalent bond if it's right on the border, okay? So that's kind of the key to this, is that if it's on the borderline, you got to kind of make a decision or at least give an explanation. Sometimes the decision is going to be easy, like the case of the KBr, right? The potassium is a metal, so it's like a dead giveaway. That's an ionic, it's an ionic substance. We know it must be an ionic bond, okay? So you have to be able to explain yourself in that situation, okay? All right, guys, well, that's it. Like I said, I promise you this is going to be a short one. I will see you guys on Tuesday, right? Thanks for bearing with me on this and watching this. But this wraps up the remainder of our notes. Monday, again, you'll get that stuff. Make sure if you didn't get your packet, review sheet, or note card, get that from the sub. The sub will hand out the trends worksheet and the take-home quiz that you guys will be working on in class on Monday. And then Tuesday, those things are due, and I'll be back, and I'll see you guys on Tuesday. Okay. Thanks again, and we'll see you guys later.